Welcome back to Arxflix. Today, we're exploring a fascinating new method in deep learning titled 2BP, two-stage backpropagation. This technique addresses a common challenge in training large deep neural networks, or DNNs, which often exceed the memory capacity of a single accelerator, thus necessitating the sharding of model parameters across multiple accelerators. The typical approach is known as pipeline parallelism, where model layers are distributed across multiple devices. However, current implementations are bottlenecked by the automatic differentiation tools provided by ML frameworks. This figure showcases the effects of different pipelining schedules with and without 2BP. Our solution, 2BP, comes into the picture by splitting the backward propagation step into two stages, thus maximizing accelerator utilization. In traditional synchronous pipeline parallelism, all accelerators flush at the end of each step, keeping the computations in sync. This incurs significant idle compute time, referred to as the bubble ratio. This equation represents the bubble ratio in a naive pipeline parallelism setup. The bubble ratio is defined as the fraction of total runtime that is idle. 2BP, or two-stage backpropagation, minimizes this idle time. It separates the computation of gradients into two stages, backward P1 and backward P2. By splitting these computations and reordering them, 2BP reduces the overall bubble ratio and idle compute time. The implementation of 2BP was built on top of PyTorch, bypassing its automatic differentiation engine. This allowed for greater flexibility in reordering computations. Figure 2 displays how we combine microbatches backward P into a single operation, optimizing the computation process even further. The researchers tested 2BP on various model architectures and pipelining schedules. Specifically, they evaluated its effectiveness using four models: Transformer 7B, BERT-Large, Mamba1, 4B, and ResNet 152 across four pipelining schedules: GP, 1F1B1, 1F1B2, and a naive approach. Figure 3 shows the throughput results for different models and schedules. In all cases, 2BP significantly increased throughput, with gains up to 170x. While 2BP reduces idle compute time, it does come with an increase in peak memory usage. Figure 4 summarizes this memory usage. The increase varies significantly based on the model architecture and pipelining schedules. The benefits of 2BP become more pronounced as we scale the number of accelerators. Using a BERT-like model, the researchers observed consistent performance gains even as the number of GPUs increased. Figure 6 illustrates the scaling effects with a fixed model size, where we see considerable speed-ups across different GPU counts. The research team plans to mitigate the increased memory usage through techniques like intermediate derivative checkpointing, which would selectively store and recompute intermediate derivatives. They also aim to explore optimizations for scenarios where pipeline parallelism is combined with data parallelism, enhancing the overall training efficiency. 2BP presents a promising advancement in training large DNNs by effectively reducing idle compute time and increasing throughput significantly, albeit with some increase in memory usage. This method provides a flexible approach to improving the efficiency of deep learning models at scale. Thanks for tuning in to Arxflix. Don't forget to like, subscribe, and hit the bell icon for more cutting-edge research breakdowns. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.